Welcome back, everyone. I hope you all did well on your test last week. You've completed the second unit of the class. And I think that you've gotten familiar with probability, at least at this point, and you've had some experience with doing some of those probability problems in Excel as well. And so I think that you'll have found that helpful. Over the past few weeks, I've promised to combine all of the ideas that we've talked about into what is the general idea of statistics, right? What you're going to be learning how to do in this class, right? Everything we've learned up to this point has uh, been about learning how to calculate measures of center and make graphs, and then talking for the last few weeks about probability. But this week we're going to finally put it all together. And so I think that you will find this lecture really helpful. And I hope that it's not too much longer than the other ones. So this week we're going to talk about how to understand the normal distribution, what it is, and I'm going to show you how to use it some in this situation. And then in the next section, we're going to expand it a little bit further. So I would like you guys to recall from last week or the previous weeks when we talked about binomial distributions, right? And I think this was probably one of your graphs from one of the assignments. If you happen to watch this video before you complete that assignment, you maybe get one of the answers here. Okay, but recall that this is our shape of the binomial distribution, right? This was our number of successes down here at the bottom, okay, and then our probability over here. This is a discrete probability distribution. And all that means is discrete just means that these x values here can only be discrete numbers, right? It can only be 1, 2, 3, 4, 5. Okay. If we wanted to find the probability of choosing just 4 or 5 people, right? So we want to know what's the probability, right, that we choose somebody in this range. Well, if you remember from last week, all we would do is we would just add up those probabilities, right? Something about 0.06, and I'm just guessing here from what it looks like. It's about 0.06, we'll say, and about 0.1, just for simplicity's sake. And if we add up those two probabilities, well, there's about a 0.16 or 16% chance that you choose between 4 or 5 people. But there's another way that we can find that same probability with this picture, right? Just by finding essentially the area of these two blocks. And you can think about it that way because each side on down here is just 1 because it's discrete. Okay, so the 0.06, right? If we find the area of each of these rectangles and we add them up, we're going to get exactly the same thing. And so we can expand this idea of probability distributions to deal with continuous variables. Okay, and so probability density curve is what you see here. Very similar to the discrete probability distribution you saw in the last slide, except now our x variable can be continuous. It can be anything between 4 and 6. It's not just those two numbers. And so from this graph, right, if we wanted to find the proportion of the population that's between 4 and 6, we can see that the area is 0.16, and that's 16% of the total area of this curve, because the sum of the probability has to be equal to 1. And so this area represents 16% of the total area. And you'd find 16% of the proportion of the population in that region. If we randomly chose a value between 4 and 6, there'd be a 16% chance that there'd be a 16% chance that if we randomly chose a value, it would land between 4 and 6. It would land somewhere in here. You can see in this case, the most likely scores are actually going to be on this side because they have the higher probability. We can look at these density curves in a slightly different way. If we want to know what proportion is not between 4 and 6, well, we can just subtract. Since we know 0.16 is between 4 and 6, And this will give us 0.84. What's the probability that it's not between 4 and 6? Well, it's the same thing, 84% or 0.84. And so the area in this case is equal to the probability of finding a value in that region. And now we can use this when we deal with variables that we can measure. Okay, and there's one specific probability density curve that becomes very important. And it's called the normal curve or the normal distribution, or sometimes the Z distribution. Okay, but it is a curve that you are familiar with how it looks. Okay, we're going to write the mathematical formula for the normal distribution. It's complicated. And the mathematical formula that defines this curve is complex, but you don't really need that. Okay, you just need to kind of know what the shape looks like. The normal distribution is what you think about when you think of something like a bell curve. Okay, it's going to be symmetric and it's continuous. Symmetric just means if you draw a line through the center, right, it's the same on both sides. In the case of a normal distribution, the mean, median, and mode are all equal. They're all going to land in the middle of your values. Okay, the distribution only has one mode. Okay, and the curve is never going to reach the x-axis. There's never a region where the probability is 0. It can be really, really, really small, be really, really close to 0, but it'll never be 0. Okay, and then the total area under this curve is equal to 1. More specifically, when we talk about the Z distribution, actually, we'll talk about that in just a few minutes. So normally distributed variables occur all the time. Okay, here we have the days before or after a due date that a baby is born. And notice that most of the babies are born at or around their due date, plus or minus 2 or 3 weeks. And then a few on the outer edges that are less likely. And notice the peak that this makes. This is real life data, but you can fit this normal curve over the top of it. There are a lot of variables where we can do this, and these variables we can then use what we understand about this distribution and probability distributions in general, and what we've learned about probability and what we've learned about means and medians. We can use all of those things to tell us something about the variables that we measure, to tell us something about the average number of days before or after the due date that a baby's born. Or, as you'll see in a lot of the other examples that come up, some of the other things that we can answer. Now, with any type of variable that we're trying to measure, we talked about means, but we also talked about the standard deviation. Right? And remember, the standard deviation is essentially the average deviation of your scores from the mean. And if we know that a distribution or a variable is normal or symmetric, we can use that distribution, that shape, this natural shape that you see in the data, to predict the probability of finding some particular value if we know how far that value is away from the mean. Okay? If we are just going to choose things randomly and ask questions. So let's say we're gonna randomly choose someone and compare their height to the average height of people in the country. Intuitively, if you just randomly choose someone, their height's generally going to be average, right? They're going to be around the average height. If you just randomly choose any person, most people are about average height. There are a few people who are really tall, a few people who are really short, but most people are about average height. most of the scores that you collect whenever you measure some type of variable like this, most of those will be found closer to the average. Okay, with very few found far away, right? You're not going to, if you randomly choose people, you're not going to randomly choose someone who's 7 feet tall. That's going to take a lot of random choices before you get to that point. Okay, but because we know the normal distribution, and we know that the way the probabilities are distributed, we know the shape of the data, we can talk about exactly how much data we'd expect to find in any region and be able to answer a whole bunch of questions if we know that the data are normally distributed or they're symmetric. Okay, and the way that we do that is by using the standard deviation, or more appropriately, the z-score. Now, we calculated these before, I think, but now I'm going to show you why they matter. And so first, let's just run back through this. I think we may have done a little bit of this before. When we want to compare data to a distribution, we can use the z-score. Recall that z-score is a measure of position that we can use when we have data that are best defined by the average, by the mean value. Right? And if you go back and watch some of the previous videos, by the values or the variables where the mean is the best measure of center. And in those cases, the mean and median and essentially mode are all equal, and you have what is essentially symmetric data, much like you've already seen earlier. Recall also that the z-score gives you the distance from the mean in units of standard deviation. So a z of 1.5 just means it's 1.5 standard deviations above the mean, or a -1 means it's 1 standard deviation below the mean. That's great to give you a measurement of position, but we can use now that position to learn something about the probabilities. How likely is it that we randomly chose someone who's 1.5 standard deviations above the mean? And so again, quickly reviewing for z-scores here, when you want to find the z-score, right, if we know the average height for a male in the United States is about 5'10" or 70 inches, right? So this is our population mean. The standard deviation of 3 inches, that's our population standard deviation. If we want to find the z-score for a male who's 6'2" or 74 inches tall, 74 is x. Subtract, and this gives us z. Okay, same for if we want to find for someone who is 65 inches tall. You can subtract the two. And remember that x always comes first. That's going to be important now and for the rest of the next section. Now, the reason why we focus on z-scores and symmetric distributions is what I've been talking about for the past few minutes. If we know the data are symmetric, we can take that normal distribution and essentially just fit it over the top of the data. And then we can use what we know about the normal distribution, what we know about the probabilities from that probability density curve, which you'll see. It's just the normal distribution over and over again. And we can then use that to find probabilities. Okay, z-scores become remarkably important and remarkably easy to use. Okay, the z distribution is slightly different from a normal distribution, and I'll show you what I mean in just a minute. So up to this point, we've talked about how to find probabilities, and I showed you how to find the probability with the areas earlier in the video. But let's talk about what we can really do with this. And so if we can assume that the data are symmetric, we can go back to that empirical rule that we mentioned before, and we can fit this to our normal distribution. And in that case, we'd expect to find about 68% of the data between plus or minus 1 standard deviation. Well, this is at the mean, z equals 0. This is z equals 1. And this is z equals -1. This is 2 standard deviations above, or z equals 2. And this is equals -2, or z equals 3, z equals -3. And so we can see that about 99% or 0.7% of your data will fall within 3 standard deviations, or within z plus or minus 3. But you can also see how we could use this to ask questions about what's the probability of finding a person above z equals 1 or below z equals -1. So there's a bunch of examples that we're going to show with that, right? And as I've said, I think I said this a few times, if it's symmetric, we can map to it. Right? We can fit the normal distribution, the z distribution, over our data. And you already know how to do that by just finding the z-score. That z value will tell you the position of a point in the distribution, and from that position you can determine the probability. We had to first learn about what probability was to understand what it is that you're talking about when you find that probability, okay, to see how the area can represent the probability. But you already know how to find the z value, which is going to give you those probabilities. Okay. So we're going to run with this example for just a few minutes. The average height of a male in the United States is about 70 inches with a standard deviation of 3 inches. Just keep these values in your head so I don't have to write them down every time. What's the probability that a randomly chosen person will have a height greater than 70 inches? Okay, well, let's look at this a couple of different ways real quick. Our mean is 70. Okay, the standard deviation is 3, so 70 plus 3 is 73. 76, 79. If we subtract 3, okay, and then let me just put this is z equals 1 and z equals -1. We'll just keep those there so you can kind of remember where these numbers go. So what's the probability that a randomly chosen person would have a height greater than 70 inches? Well, here's 70. Okay, well, anything greater than 70 inches is on this side of the graph. Since 70 is the mean, we don't have to do this quite yet, but you would add all of those up. There's a 50% chance. If you randomly choose someone, okay, there's a 50-50 chance that they're above or below the mean, above or below the average, right? They could be exactly the average, maybe. Okay, and as you'll see, we will not talk about how to calculate exact value probabilities. So what's the probability that you choose exactly a person who's exactly 70 inches? Because how do you even determine that? Might it be between 70.0 and 70.5, or it's where are the values that you would use, right? And you'd have to have some kind of range there, and then you have to use calculus and integrate to find the area. It's too complicated. We're not going to deal with that. This is the much simpler way of understanding. It doesn't involve having to do any kind of calculus. Okay, so instead of finding exact values, the questions are always going to be above. So what's the probability someone's going to be greater than a value, less than a value, right, or between two values? And that's what you'll see a lot of in the next examples. Right, so what's the probability that a randomly chosen person will have a height greater than 73 inches? Well, if this is 70 and this is 73, now we want to know greater than 73. Well, that's all of the area on this side, above 73, above z equals 1. And so we could just add all of those up, 13.59, 2.15, 0.13. If we put this into a calculator real quick, 13.59 plus 2.15 plus 0.13, 15.87. And so there's a 15.87% probability that your value is above 73. Now here we're using the predetermined probabilities that are given in this picture. It's not always that easy, as you'll see. But the goal here is to show you how the area represents that probability. What if we were looking for a height less than 76? Well, again, 70, 73, 76. Less than 76 is everything over here. Okay, and there's a couple of ways that you can do this to find all of this area. Okay, but we know that it has to add up to 1 or 100%. And so we can really just do 100% minus these two. So minus 2.28, which should give you 97 something. 100 minus 2.28, 97.72. And if you add all of these up, you should still get the same answer. Either way works. You still get 97.72. But we can find the probability by finding this area. And we can do this again if we want to find the value between 64 and 73. Where's 70, 73, right? This was 76. Again, z equals 1 here. 67, 64, z equals 2, or sorry, negative 2. And so we would just want all of this area, all of the stuff in between these two lines that we've drawn. Right, the z values can mark our position in the distribution, and then we just find the area between those two positions, right, or above or below that position. And in this case, you would just add up 34.13, 34.13, and 13.59. We add all of those up. $81.85. Not every value, though, that you're going to want to find is going to be exactly on a particular value, right? It's not going to always land on one exact standard deviation. Okay. For example, if we wanted to find the probability of someone who was 75 inches taller, well, where's 75 here? Is it, is it there, I guess? And then how do we find those areas without being exactly there? Okay. And the trick here, and this is true for all of the values, is that it's always easiest to convert everything into z-scores. Okay, because while the distribution, the numbers here are different each time, depending on whether we're talking about height or some other variable, the z-scores, the position of z will never change. Okay, if it's one standard deviation above the mean, doesn't matter what the variable is. It's one standard deviation above the mean. That probability is the same. And so we can transform everything into z-scores or z-values and then use those z-scores to determine the area. Okay, so if we wanted to find 1.67 standard deviations above the mean. So we know in this case that z is 1.67. Okay, I think I put the wrong table in here, but I'll show you. Oh, well, I'm going to show you how to use this. Okay, we can find the probability different ways. Okay, there are z-tables that should be available this week in your folders. It should be this table here. Okay, this table A2, I believe, is what it's labeled. Maybe in your textbook as well. And I'm going to show you a little bit how to use this in some examples. Okay, but you can also use Excel. Excel will calculate these probabilities very easily for you. There are two different functions that you'll need. And so I'll show you those throughout, and I'll try to show examples with Excel as we go through in this video. So the first thing that you need is this command, which will give you the probability given the z-score. Okay. And it gives the probability to the left or below. If you want to find the probability above, you just have to do 1 minus the value. Okay, so it's the same command, it's just 1 minus. And you'll see some of this as we go through in some of these examples. So the average height of a male in the United States is about 70 inches with a standard deviation of 3 inches. Okay, assume the height's normally distributed. What's the probability that a randomly chosen person will have a height, is what it should say, less than 63 inches? Well, here's our X value, 63, minus 70 divided by the standard deviation. That gives us a Z-score of negative 2.33. So what these tables do is if you have the distribution, and we'll have some actual pictures in here in a second, so I don't have to draw it all the time. It always gives you, it always gives you the area to the left of Z. If we want to find the Z-score, for which the area to the left is 0.65, again, we can use the table or Excel. Here we're looking for where is this area, right? We want Z. So where is this area to the left, 0.65? Okay, and so we can look for where we find the area closest to 0.65 on the table, which is going to be somewhere between these two. Okay, between 0.38 and 0.39. Okay, and in fact, if you type it into Excel, this is the other command that you'll need, which is just the, here you will type in the area to the left, and it will give you the Z value. And so Z would be equal to, in this case, 0.385 or 0.38. And we can do the same thing if we want to find that. This would be 0.82. And so if we want the area to the left to be 0.18, we're going to look for where the area is closest to 0.18. Again, here I left off the thing, but 0.000102. So it should be negative 0.92, or between negative 0.91 and 92. And again, you can use that same command in Excel, but because you want the area to the right, then you want to subtract the areas here. Okay, because you want to know, you want to do 1 minus the area to the right so that you can find the area to the left. You also could have just plugged in 0.18 here, and you would have gotten the same answer. We want to find the Z-scores that bound the middle 70% of the area under the standard normal curve. Right, well, the middle 70% means 0.15 on this side and 0.15 on this side. This would be the middle 70%. But it's not always that easy in Excel to figure out, or on the tables to figure out those exact boundaries. Okay, but we can do it. If we want the boundary for 0.5 to the left, we can use our Excel command that will plug in the area to the left, 0.15, and we get Z of negative 1.03. If we want 0.15 to the right, that means there's 0.85 to the left. We can plug that in here, and that'll give us the upper boundary. Also, if the areas are the same on both sides, then these Z values will always be the same on both sides. And so you only really need one, and then it's just plus or minus. So now let's look at some more examples that are related to some more real life examples. Fluorescent bulbs are more energy efficient, but they take longer to reach full brightness. The time it takes for a compact fluorescent bulb to reach brightness is normally distributed with a mean of 29.8 seconds and a standard deviation of 4.5 seconds. We randomly select a bulb and it takes 28 seconds to reach full brightness. Let's find the z-score for x equals 28. Well, in this case, z equals 28 minus 29.8 divided by 4.5. And that's going to give us a z-score of negative 1.8 divided by 4.5. Negative 0.4. So 0.4, oh, sorry, negative 0.4. Going to be about right here. Might use this red color, it looks a little better. And so that's going to give us that position there. And we could find this area to tell us whether it would be less than that amount of time or greater than that amount of time. We'll see some more examples like this. Yeah, but it identifies the position and it tells us that having a small z-score means it's close to the mean. Okay, let's not dive into the probability just yet because we didn't ask that just yet, but there's probability answers here too. The probability of randomly choosing a light bulb that's less than 28 seconds. Okay. And you can find the probability that it's greater than 28 seconds. Okay. By just splitting the distribution where you found the variable. And we'll see more of this in just a second. Suppose pulse rates among healthy adults are normally distributed with a mean of 81 beats per minute and a standard deviation of 8 beats per minute. What proportion of healthy adults have pulse rates that are more than 89 beats per minute? Well, if we want the proportion, right, we need to know the area or the proportion of the area that's in that region in our normal distribution. Okay. We're interested in 89 beats per minute. So the z-score, 89 minus 81 divided by 8. Is that just 1? That is just 1. Your z equals 1. Then we want all of this area. I'm sorry, we're looking for above, more than, sorry. We want all of this area to find the proportion that will have more than 89 beats per minute. This is not as simple as just knowing this, or you have to use the table or you have to use Excel. I'm going to try something here, which I think I can do this. Bear with me for just a second. Okay. We want the area that is above z equals 1. And so we should be able to do that by finding 1 minus, sorry, equals 1 minus the area below z equals 1. And so this proportion of the area, 0.1587 or 15.87%. Let me point something out real quick. Where's it at? It was the very first question where Z was equal to 1, 15.87%. They're the same answer because the Z values are the same. Okay. We have a conservationist organization that monitors the health of whale and dolphin populations. Here we have a normal distribution. They're modeling the lengths of blue whales that will be born. Okay, so it's the length of a whale. They're using a normal distribution with a mean of 279 inches, a standard deviation of 40 inches. We want to find the percentage of blue whale calves that are between 317 and 341. Well, here now we're going to need two Z-scores. And we're going to need one for the lower one and one for the upper one. We're going to find between two values. Now I drew them in the wrong place there because they're both above the mean. But let's calculate them. Try a slightly different color. Nope. Okay, so for the lower boundary, 317 minus 279 divided by 40. That will give us our lower Z-score, 317 minus 279 divided by 40. That's 0.95. So that's about right here. And then for the second value, 341 minus 279 divided by 40. And so our X value minus the mean divided by the standard deviation. And we get 1.55. And so these are the two boundaries that we're interested in. Now, if we want the area between, right, again, we're going to have to either use a table or we can use Excel. Okay, and let me show you, we can do this slightly differently in Excel and maybe save a little bit of the questions here. If we move, or if you recognize, we want the area to the left. First of all, our first value will give us the area to the left of Z1. Second value will give you the area to the left of Z2. If we subtract the two, then you'll get the area in between. And so if we do equals of our upper Z value, this gives us the area to the left of Z2 minus the area, to the left of Z1, which in this case is 0.95. And we hit enter. The area here is then 0.1105 or 11.05%. So what's the percentage of blue whales with that length? About 11% will fall in that range. The lifetime of a certain type of tire in thousands of miles is normally distributed with a mean of 40, so 40,000 miles essentially. Standard deviation of 5, so 5,000 miles. What's the probability that a randomly chosen tire has a lifetime greater than 49,000 miles? So in this case, X is 49. We're going to find our Z-score, 49 minus 40. divided by 5. That's 9 divided by 5, which is 1.8. And so we want to know what's the probability of a tire being chosen with more than 49,000 miles or having greater than 49,000 miles, or a z-score of greater than 1.8 or 1.80. So we want this area here. Greater than z equals 1.80. Again, I'm just going to insert this Excel table because this seems to be working okay. Kind of probably looks a little strange in the video, but you should be able to see what I'm calculating. If we want the area that is above 1.80, then we need to do 1 minus the area below 1.80. Oh, and you want to put equals in front of it, or else it won't do anything. 0.0359, or 3.59%. So there's a 3.59% probability that if you randomly chose a tire, it'd be greater than 40,000 miles. A few more examples. Suppose scores on a particular test are normally distributed with a mean of 130 and a standard deviation of 20. The minimum score needed to be in the top 15% of the scores on the test. Well, that means that we want to know what's the z-value where we will find the top 15%. And now we actually figured this out in another example way back. Let me find it here. Right, there's 15% above. 1 point z is going to be 1.0364, or we'll just call it 1.04. Okay, so here our z-value from that previous example, 1.04. Okay, if we want to know the minimum score on the test to get in the top 15%, okay, then we have to take our z-score and our mean and standard deviation and calculate x. Remember, x equals the mean plus z times the standard deviation. And so that is the mean of 130 plus 1.04 times 20, which is 130 plus something I can't do in my head. 20.8. You would have to score on the test a 150.8 to be in the top 15% of the scores on the test. A couple more like this. In a recent study, the CDC reported that blood pressures of adult women are approximately normally distributed with the mean of 80.5 and a standard deviation of 9.9. We want to find the 40th percentile. Okay, well, remember the 40th percentile is the point at which 40% of the data is below that point, right, and 60% is above. Okay, so we want to find the area to the left where we have 40%. Now we have to use Excel to find, I don't know why it always inserts there. Here we have to use Excel to find not the area to the left, because we know we want the area to be 40% or 0.4. But we want the z-score. So we're going to do equals norms and then INV, right? It's the inverse. Okay, now it asks for the probability. We want the probability to the left to be 0.4, and this will give us our z-score. And so that z value now, negative 0.25, we'll just call it 0.25. And then again, to calculate the blood pressure value, to find x, it's going to be the mean plus z times sigma, or the z times the standard deviation. So 80.5 plus negative 0.25 times 9.9. 80.5 plus something minus something. Negative 2.475. You get 78.025, or probably just call it about 78 in this case. So the 40th percentile would be about 78, whatever units blood pressure is measured in. Use Excel to go from the probabilities to the z-scores and from the z-scores to the probabilities. And then do the rest by hand because it's much easier to do it that way. Last example in this section. Scores on a statistics final in a large class are normally distributed with a mean of 75 and a standard deviation of 8. Between what two values are the middle 60%? Okay, well, again, middle 60% means there's 40% split, so there's 20% above, or 0.20, 20% below. Because it's symmetrical, we only need the one command in Excel to find the z-score. I just wrote the command down. I don't know why I didn't insert the other thing, but I wanted you guys to see it. We only need this to find both of our z values, because remember, this distribution is symmetric, so equals norms. Now we want the area to the left to be 0.20, 20% above, 20% below. We want the middle 60%. That gives us z of negative 0.84. Which means we'll also have z of positive 0.84 will be our other boundary. And it's going to be all this stuff in the middle here. That middle 60%. I think I've drawn that very badly on the graph. Not entirely. Just a little more this way. So now we just want to find those two scores that bound those two regions, right? So what do you have to score on the test? And so again, same formula, z times the standard deviation, 75 plus negative 0.84 times 8. This will give us our bottom value. 0.84 times 8 is 6.72, so 75 minus 6.72, 68.28. The upper boundary, (75) plus 6.72, 81.72. And so if you make between a 68 and an 81, that will be the middle 60% of the scores, given that mean and standard deviation. Now notice that in this section, we've talked primarily about single individual scores. Above or below one value, we're randomly choosing one thing. Okay, but that in statistics, we do more than just choose one thing, right? We sample more than one thing. In the next section, I'm going to show you how this exact same idea relates to sampling with a slight change. and hopefully without all of the issues of the videos getting broken up. If there were some issues in this and you had some questions, please let me know, and I'll be happy to try to clear them up in the videos. I will edit some of these things out to try to correct some of the dropouts that I had. But in the next section, we'll talk about how all of this relates to samples, and we'll be well on our way to understanding how we can answer a lot of questions using statistics.